Hello, future physicists. Hi, everyone. It's me, Professor Atom. And today we're embarking on an exciting journey into the world of electricity, where incredible discoveries await us. Imagine that the world around us, from the tiniest dust specks to massive galaxies, is made up of tiny particles. And these particles, just like you and me, can be charged. Let's look at our favorite characters. Here's SpongeBob SquarePants, who just touched a fluffy sweater and feels his hair stand on end. And here's Elsa from Frozen, who can create amazing sparks with her magic. What's happening? It's all the magic of electric charges. What is a charge? Imagine that our particles have a special superpower, an electric charge. This charge comes in two types. Positive charge, like Superman, always ready for action. Negative charge, like Batman, who likes to operate in the shadows. But here's the secret. Different charges love each other. It's like SpongeBob and Patrick. They always attract. If we have a positive charge and a negative charge, they'll pull towards each other. Same charges don't like each other. It's like Tom and Jerry. They always try to push each other away. If we have two positive charges or two negative charges, they'll repel. Coulomb's law. How much force is in that love? Now, for the most interesting part, how do we know how strongly our charges attract or repel? A brilliant scientist comes to our aid. Charles Augustin de. He was like a real detective who unraveled the mystery of the force of interaction between charges. He discovered that the force with which charges interact depends on two things. The magnitude of the charges. The greater the superpowers of our heroes, the stronger they interact. Imagine Hulk and Thor have huge charges. Their interaction will be incredibly strong. If Pikachu has a small charge, the interaction will be weak. The distance between them. The closer our heroes are to each other, the stronger they feel their love. If Simba and Nala are very close, they strongly attract. If they are far from each other, their interaction becomes weaker. Here's how Coulomb described it in his magical formula. F equals K, R2, Q1, Q2, where F is the force of interaction measured in newtons. Q1 and Q2 are the magnitudes of our heroes' charges, measured in coulombs, named after Coulomb, of course. R is the distance between the charges measured in meters. K is a magical number that helps us calculate everything. It's always the same. 9, 10, 9 nm, 2, C2. Don't worry if this formula seems complicated. The main thing to remember is the larger the charges and the smaller the distance, the stronger the interaction. Where do we see Coulomb's law in life? Coulomb's law is everywhere. When you pet a cat and your hair gets static. That's it. When you see lightning, that's a huge electrical discharge interacting with the earth. In your phone, computer, TV, tiny particles interacting according to Coulomb's law are working everywhere to transmit information and light. So, friends, electricity isn't just sparks. It's a whole world of interactions governed by the amazing Coulomb's law.
Elementary particles and charge interaction in nature. We already know that all substances are made up of tiny particles that can have an electric charge. But what exactly are these particles? Let's figure it out. Elementary particles with different charges. Imagine that the world around us is a giant construction set. Its smallest bricks are elementary particles. Some of them have a charge, while others do not. Positively charged particles, proton. This is a very important particle found in the nucleus of every atom. It has a positive charge, and the number of protons determines what chemical element it is. Imagine a proton as a tiny leader in the atom's nucleus. Positron, this is the antipode of the electron. It has the same mass as an electron, but an opposite charge. It's like a superhero and their villainous double. Negatively charged particles, electron. This is a very light particle that orbits the atom's nucleus. It has a negative charge. It's electrons that move when a light switch turns on a bulb, creating an electric current. Imagine electrons as very agile helpers who do all the electrical work. Particles with no charge. Neutron. This particle is also found in the atom's nucleus along with protons, but it has no electrical charge. It's like a silent guardian that helps the protons stay together. Photon. This is a particle of light. It has no mass or charge but carries energy. When you see light, these photons are traveling to your eyes. Neutrino. These are very mysterious particles that barely interact with matter and have no charge. They can fly straight through the entire Earth without even noticing it. Interaction of charges in nature. Magic around us. Coulomb's law, which we talked about, works not only in the laboratory, but throughout the entire universe. Here are a few amazing examples. Lightning. This is perhaps the most impressive example of charge interaction in nature. During a thunderstorm, water droplets and ice crystals in clouds rub against each other, causing some particles to become positively charged and others negatively. Typically, negative charges accumulate at the bottom of the cloud and positive charges at the top. When the potential difference becomes very large, a huge electrical discharge occurs, lightning, which can punch through the air to the ground or between clouds. It's a true giant flash of electricity. Auroras. This is one of the most beautiful natural phenomena. When charged particles from the sun collide with atoms and molecules in Earth's atmosphere near the magnetic poles, it causes these atoms to glow in different colors. This happens due to the interaction of electric charges. Imagine it as a light show put on by charged particles. Electrification by friction. What we did in class with the rods and wool also happens in everyday life. For example, when you take off a wool sweater, you might hear crackling and see small sparks. This happens because friction causes electrons to move, and different charges accumulate on the sweater and your hair, which then interact. Formation of chemical bonds. Even in how atoms form molecules, Coulomb's law is hidden. Electrons are attracted to positively charged atomic nuclei, holding them together and creating chemical bonds, like invisible electric glue that connects everything in the world. Nervous system function. In our own bodies, there's a constant movement of charges. Nerve impulses, which allow us to think, move, and feel, are transmitted by the movement of ions across cell membranes. It's like tiny electrical signals traveling along the wires of our body. So electric charges and their interaction are not just an interesting phenomenon. They are a fundamental part of our universe, governing many processes around us and even within us. Laboratory work. Feel the force of charges. Objective. To investigate the interaction of similarly and oppositely charged bodies. Equipment. Ebonite rod, glass rod, piece of wool. Piece of silk to light pith balls. Suspended side by side on threads. Stand for suspending the balls. Procedure. Preparation. Suspend 2 light pith balls on threads so they barely touch each other. Ensure there are no strong air currents around. Experiment 1. Charging the balls similarly. Step 1. Take the ebonite rod and rub it vigorously with the piece of wool. Step 2. Carefully touch one of the pith balls with a charged ebonite rod. You will see the charge transfer to the ball. Step 3. Repeat step 2 with the other pith ball, touching it with the same charged ebonite rod. What do you observe? Record your observations. Experiment 2. Charging the balls oppositely. Step 1. Discharge the balls. Step 2. Take the ebonite rod and rub it vigorously with the piece of wool. Touch one of the pith balls with it. Step 3. Take the glass rod and rub it vigorously with the piece of silk. Touch the other pith ball with it. What do you observe? Record your observations. The balls will attract each other as one has acquired a negative charge and the other a positive charge. Analysis of results. Draw conclusions. About the interaction of similarly and oppositely charged bodies, based on your observations,